Hello, welcome back. When servicing brake systems, there are a number of different measurements and things to inspect. One of those items is the friction surface that the friction material rides against. On drum brakes, our friction lining is on a shoe and it rides on the inside surface of a drum. And on disc brakes, we have a rotor with a pad on either side clamping down and applying stopping force to the friction surface on the rotor, the front and the back.
Each vehicle is going to have its own manufacturer specified tolerance for how much material can be removed before either that rotor is too thin or the diameter across the inside of the drum.
As material is removed from this friction surface on the inside of the drum, it's going to increase in diameter as material is removed from that surface. As material is removed from the friction surfaces on a rotor, that is going to decrease the overall thickness. So rotors will come with a minimum thickness specification and drums will come with a maximum diameter specification. Minimum thickness specifications for a rotor or disc brakes are set to prevent the piston and the caliper from coming out too far. If the piston comes out too far, it may not retract correctly, and worst case scenario, brake fluid can come out of the caliper body and lose hydraulic pressure on that part of the circuit. On drum brakes, the maximum diameter specification exists to prevent the wheel seal cup seals from coming out of the wheel cylinder too far. Same thing could happen. If the cup seals come out too far from the wheel cylinder, brake fluid can leak from the wheel cylinder and that part of the circuit would then be compromised due to lack of fluid. These tools shown here are used for measuring disc brakes and drum brakes. Disc brakes are measured across the rotor thickness with this outside caliper. Notice it has a point on one side and a flat anvil on the other side. Drum mics can be either metric or standard. Depending on your specifications will determine which method you use to measure them. If your specifications are in inches, you'll measure with an SAE standard drum mic. If your specifications are in millimeters, you will measure with a metric micrometer. The drum micrometer is comprised of a couple pieces. Each of these sections can move across the barrel on the track. The track is a groove cut in the backside of the barrel. The part that measures is on the dial indicator on this side. As the button is depressed, it will give us a measurement. But our measurement isn't very large. So the drum mic has to be set up correctly before we take a measurement in order to get an accurate result. The specification for this drum, maximum drum diameter, is 225.55 millimeters. We're going to use the metric drum mic to measure the inside diameter of this drum. In order to make an accurate measurement, these can slide on their detents to different scales on the drum mic barrel. There is a little bit of wiggle room there, so these must be tightened down and snugged in order for there to be no play across the tool in order to measure correctly. If these were loose, we would have deflection out here where it's trying to take a precise measurement, and our measurement would be inaccurate. On this barrel, we have a smooth center section, and then we have the teeth for the detents on either side. The numbering comes to the middle and starts at 15 at these two lines. To the right, we have larger gaps, and our numbers increase by odd numbers. On the left, we have tick marks in between the longer dashes, and again, it increases by odd numbers. On the other side of the barrel, there are even numbers, and just like the other side, one side has blank areas in between the hash marks, and the opposite end has smaller tick marks in between the larger gaps. To recall our specification, maximum drum diameter 226.55 millimeter. In order to measure this, we need to start with what we know. Our drum specification is 226.55 millimeters maximum. On the barrel, these are noted in centimeters. So to convert to millimeters, for example, 17 centimeters in millimeters, we would move the decimal place to the right one space. So 17 centimeters equals 170 millimeters. The numbers are the same on both directions. Since our specification is an even number, we'll work from the even side. 226 millimeters is the same as 22.6 centimeters. To set this up correctly, we need to bring each side to 220, or 22 centimeters. Now we can check our fitment into the drum, and as you can see, we're not quite out to the point where we can make a measurement. So let's go to the next centimeter, 23 and 23. Now we can't even fit the tool into the drum to measure it. So we're somewhere in between 220 millimeters and 230 millimeters. So we're set back to our initial measurement of 220 millimeters, or 22 centimeters. Once we've set this to center, and we have our base, and we know we're within 1 centimeter of distance before we can measure the drum, this side doesn't move. The side with the small hash marks in between the larger marks is the only side we move at this point. So on the metric drum mic, as we move this out, starting at our 22 mark, every notch that we move it equals 2 millimeters. So if we start at 22.0, or 220 millimeters, and we move it 1 mark, that becomes 22.2 centimeters, or 222 millimeters. Still not enough to make the measurement. The next mark will be an additional 2 millimeters. So we will be at 22.4, or 224 millimeters. Still have a gap. Move it again, tighten it down. And here we are getting a measurement. In order to take an accurate measurement of the diameter of the drum, we need to take that measurement directly across the center of the drum, and it has to be at the same depth. If we're at a different depth, that would skew our measurement. And if we were not directly across center of the drum, that would also skew our measurement. So in order to find the depth, we press down on both of these, and that sets our depth evenly. Now as we move it and sweep it back and forth, we can see our needle reach a maximum. That maximum is where we know we are directly across the center. Now to recap, we set our barrel at 220 millimeters as a base, or 22 centimeters. We moved this over a total of 3 notches, 1, 2, and the third is being covered by the edge of this piece. And each mark, each of the small marks, represents 2 millimeters. So 22.0 plus 0.2, 0.2, 0.2. So we're at 22.6 centimeters, or 226 centimeters. When the button is depressed on the gauge and the needle is on 0, that is 226.0 millimeters. And then from our 0 mark, if we go anywhere to the left, we add that. And anywhere to the right, we subtract it. Notice the -1. So the 1, the 2, and the 3 represent 1, 2, and 3 millimeters. So each dash in between there is 1/10 of a millimeter. So our drum mic is set at 226 millimeters, or 22.6 centimeters. And then we add 2.123. 2.3 millimeters to our original setting. The specification is 226.55 millimeters. Our actual measurement is 228.3. Our drum mic is only accurate to the 1/10 of a millimeter, but our specification goes to 2 decimal places on the millimeter. So that second decimal place is occupied by a 0. We do need to include it in order for it to be accurate. So our measurement specification at 226.55 millimeters and an actual measurement at 228.30 millimeters means that we are over specification on our diameter, which means that this drum is no longer safe to use and it must be discarded. There's another measurement that we need to take if this is to be considered usable or not. So if we were hypothetically within specifications on our first measurement, our second measurement would have to be perpendicular to that. By taking measurements one way across the diameter and then again 90 degrees to that measurement, then we're measuring for out of round. When we're measuring for out of round, we're trying to determine if the drum is a consistent circle all the way around. Let's call this diameter 1 and this one diameter 2. If D1 is equal to D2, okay. If D1 does not equal D2, then how far apart are they? And our general rule for out of round is 3/1000 of an inch, 0.003 inches. If we're over 3/1000 of an inch, our out of round spec is too far and the drum gets discarded. So if we have a difference in our diameter measurement of more than 3/1000 of an inch, then we are out of round and the drum is not usable. Also, if there is scoring greater than 60/1000 of an inch, meaning that there are grooves in the friction surface. So imagine a cross section of the drum. If we have grooving in here, let's say that our friction material wore down too far and a rivet contacted the friction surface of the drum. If that's the case, it might have put a groove in it. And if that groove is deeper than 60/1000 of an inch, then that drum is also not usable. After all machining is done, it should be checked back again and compared to spec. So measure before you machine it, and measure after you're done machining to make sure that it is still within its specifications and that it can still be used. The drum friction surface needs to be parallel from one side to the other. So looking at a cross section, these two surfaces that the pad rides against, which is actually one surface that goes all the way around the inside of the drum, needs to be parallel. If the drum has been distorted, those might be bell mouths, so they might taper out towards the edge. This is an exaggeration of what you're looking for, but this would change your measurement depending on the depth, how far down into the drum you measure it. So newer drum mics will actually have 2 depth settings that you can set to 2 different depths and check and make sure that your measurement is consistent. rather than having a larger diameter near the edge or the surface and a smaller diameter towards the bottom. When drums are being machined, imagine this is our cutting arm going into the inside surface of the drum. During the machining process, the drum is chucked on a lathe and the lathe is turning the drum around and around. Then a cutter is coming in from one angle and it's cutting into the surface of the drum that's passing by it, and it slowly moves its way out. So as the drum is spinning on the lathe, the cutter starts on its path down towards the inside of the drum, and as that's rotating around, it gradually moves out to the outside. During this time, we're taking out X amount of material. So we're taking this diameter and we're removing material from one side of that diameter. So half of the diameter is the radius. 2 of the radius equals the diameter. If we're removing material from the radius, that means that distance from center to the edge of the drum, or from the center of the drum to the friction surface, is going to increase. So if we increase our radius by a certain amount, we're actually increasing the overall diameter by double the amount that we're removing from that surface. So when we're calculating how much material to remove, we have to remember that removing material is always doubled on a drum. So when we check for our maximum diameter, we're checking the inside, ideally at 2 different depths, in case these are bell-mouthed. We're inspecting for condition on the friction surface. This has been recently machined, so it's nice and clean, and that's about the finish you're looking for when you machine them. There can't be any hot spots, which would be darkened areas, and hot spots occur during the casting process of the steel itself. There can be an air pocket somewhere trapped inside the casting, and the heat from breaking can cause that little air pocket inside to overheat, and that will cause a burn in the surface of the metal. And those burns are actually hardening that surface. So bringing a cutter across that surface, if it had a hot spot, would damage the cutter, and you'd have a consistent, nice finish up until that hot spot, and then from that hot spot on, you'd have a rough finish from the dulled cutter. So hot spots are hard and they damage cutters. Also, inspect for cracking. It can be somewhat normal to see tiny, tiny little cracks on the surface. They're superficial and they don't go very deep. Usually they clear out within the first pass when cutting. If there are any of those present, make sure that they're not present after you finish your last cut. If there are cracks that go through the metal, that go through and you can see them pass from one side of the edge to the other side, that means that the drum is cracked and it cannot be reused. Remember, the drum should ring like a bell. If it doesn't resonate like that, you can assume that there's a crack somewhere, and that's an indicator to look further into the condition of the drum. The next part we're going to get into is measuring and machining rotors. A couple major things that are defined on a rotor are thickness variation and runout. The first one I'm going to cover is runout. So a rotor on this model should have very little to no runout. The runout has to do with the rotor spinning true without any wobble. This is an example of exaggerated runout. This condition would result in a vibration of the vehicle when the brakes are applied. It may be felt when the brakes are not applied, and as you increase pressure on the brakes and the faster you travel while depressing the brakes, this would be more pronounced and the vibration would be harsher. So this is runout. Runout can maintain the same thickness between the two faces all the way around, but the rotor can be distorted to the point where it is giving this behavior on a very minor scale. Measuring runout is done with the dial indicator and the wheel removed from the vehicle so the exposed rotor is able to be rotated and measured against. Reinstall a couple lug nuts opposing each other so it's an even clamping force. Ideally put all the lug nuts back on, but it's not always necessary. With the dial indicator mounted properly, try to zero it at the bottom of your measurement. If you can't zero it, just watch between the hash marks and determine how far the needle is moving rather than the actual number that it's reading on. Then rotate the rotor around until you see the needle go out to its maximum and come back to its minimum. It should occur within 1 revolution of the rotor. And at the lowest point, we're at 0. And at the highest point, looks like we're between 5 and 6 thousandths. Looks like our maximum is just over 5 thousandths. Our runout spec is 3 thousandths of an inch. If we're greater than 3 thousandths of an inch, the rotor needs to be machined. So this rotor would need to be machined as long as it passes the minimum thickness specification. The minimum thickness measurement on a rotor is from one side of the friction surface measured across the thickness to the other side. This measurement has a minimum specification to prevent the pistons coming out of the caliper too far. Since it was hard to read, I highlighted where the min thickness is stamped and cast into the inside of this rotor. This one says min thickness, 26 millimeters. Now we can assume that means 26.0 millimeters. If our measurement is 1/10 less than 26 millimeters, we are beyond spec. Now look at where the pad rides on this surface. It doesn't ride all the way to the inside and it doesn't ride all the way to the outside. So that means that this surface in between here is going to be a little bit lower than the ridges on the outside. Which means that a standard caliper type measuring tool will not be able to measure accurately since there's going to be a gap. We need a tool that will actually reach around and measure the surfaces that we need to measure. This is where we use our outside micrometer. Now this micrometer is in inches. Our spec is in millimeters. So we'll have to do a conversion when we're done measuring since we don't have a metric outside micrometer. So we'll take our measurement here. And then we'll take a measurement here and find the thinnest area. Using the 0.3 inch to 1.3 inch range brake rotor micrometer, we are sitting at a current measurement of 1.016 inches. Our minimum thickness specification on the rotor is 26 millimeters. 1.016 inches converted to millimeters equals 25.8 millimeters. After taking some measurements on the rotor, we haven't measured thickness variation yet. We have a specification of 3 thousandths of an inch on our runout and an actual measurement of 5 thousandths of an inch runout. So based off of that, the rotors need to be machined. Then we have the minimum thickness measurement. Our specification, 26.0 millimeters. We measured it in inches and converted to millimeters to match the specification and came up with 25.8 millimeters. 25.8 is less than 26 and 26 is the minimum. So at this point, they cannot be machined and reused. Manufacturers may also include discard thickness, machine to thickness. The reason why they will have different thicknesses and specifications here are because as the pad wears, it wears into the metal surface of the rotor. This is to compensate for how much thickness is going to be lost over the duration of the brake's life. So the discard specification is usually going to be the same as the minimum thickness. The machine to thickness is usually going to be a little larger than the minimum or the discard. Pay attention to these numbers because at the next step, when we measure thickness variation, it requires 8 measurements around the rotor surface. Through the measuring process, we may end up in a situation just like this, but on a normal car, where we see our reason for machining right here on the run out, but our minimum thickness means that we can't use these rotors no matter how much we machine because it's only going to get thinner and thinner. 25.8 is less than 26.0. So based off of those measurements, we know that the rotors need to be discarded and replaced. There's no reason to go forward with any other measurements or any other inspections on the rotors themselves, because based off of those two, we know that we cannot machine these rotors. Parallelism, or thickness variation, has to do with measuring between the two faces, measuring the thickness between the two faces at 8 different points around the rotor to determine if there's a difference in thickness all the way around. Thickness variation is different than runout. We're allowed a larger tolerance on runout than we are on thickness variation. Thickness variation will act directly against the pads rather than the calipers soaking up some of that movement from the runout. The thickness variation will transfer energy directly back into the pads, which are being applied by hydraulic pressure. Any variation in hydraulic pressure feedback from the brakes back to the driver is going to result in vehicle vibrations and pulsating at the pedal. So we're going to mark our rotor in 8 spots. Our rotor has been marked at 8 locations all the way around for us to reference when we do our measurements. In order to measure to the 10,000th of an inch, we would need a vernier micrometer. Since we don't have a vernier micrometer, we're going to take all of the same measurements and compare them. If it's out of spec on this scale, it will definitely be out of spec on a more sensitive scale. So our first measurement is 1.017 inches. The next measurement is also 1.017 inches. The third measurement is a little bit more than 1.017 inches. It's almost halfway between 17 and 18, so why don't we just call that 1.0175. Fourth measurement, 1.017 inches. Fifth measurement, 1.017 inches. The sixth measurement is 1.0165 inches. The seventh measurement, 1.016 inches. The eighth and final measurement is 1.016 inches. After subtracting the largest and the smallest numbers from our 8 thickness measurements, our greatest difference comes to 15 10,000ths of an inch. That's 3 times our specification tolerance of 5 10,000ths of an inch. So a rotor with 15 10,000ths of an inch thickness variation, or parallelism, would likely have been a pedal pulsation and vehicle vibration concern from the customer. If you find out early on, within some quick measurements, that the rotors need to be discarded, then there's no reason to go through all the rest of the measuring to find out if they're usable still. If you know they can't be used, you know they need to be discarded, recommend replacement of the rotors. So rotors that cannot be machined. Too close or thinner than minimum thick, at or below the machine to thickness, at or below the discard thickness. If there are hot spots, some minor heat checking is okay. Around here, this darker glazing area can still be machined. Even if it had a little bit of spottiness to it, there aren't significant heat checks. You can see a little bit right here and right here. That's okay, that could be machined. We cannot machine major cracks, we cannot machine hot spots. Again, hot spots are developed by the casting where there's an air pocket inside of the casting, and that air pocket heats and burns the metal around it, and that metal becomes hardened, and that will destroy a cutting bit. So they cannot be machined. This rotor is an example of excessive scoring. Scoring is when brakes go metal to metal. So the friction wears through down to the rivets. Here's the back of the pad. Here's what's left of the front of it. So the scoring is what happens when the metal backing plate contacts the metal rotor surface. This is excessive scoring. Yeah, it's pretty much gone. You can see the profile of the vents in between the two friction surfaces. This had to have been making a lot of noise for quite some time until it was finally brought in for a concern. And I'm not sure they brought it in for a brake concern when they did. Maybe the piston got spit out of the caliper and they were left without brakes on one part of the vehicle. I don't know. But people will drive their vehicles to the bitter end sometimes and incur some pretty creative damage. A lot of manufacturers now recommend only to do on-car brake lathe servicing if the rotors are going to be machined. And this can happen with brand new rotors too, because brand new rotors can have runout and they can have thickness variation, and if it's out of spec, it needs to be true to the vehicle. Depending on the type of calipers that are on the vehicle is going to determine how you have to machine the rotors. If you have fixed calipers, there is no movement of the caliper. It's a rigid body mounted to the suspension component. The only thing that moves in a rigid caliper, in a fixed caliper, are the pistons. So on a fixed caliper vehicle, for the rotor surfaces to be machined, they have to have the same exact amount removed from one side as they do from the other side. For other types of calipers that are sliding or floating, the cutting is done at the same time. Sometimes you'll reach a smooth pass on one side before the other. You can back the cutter off of that one side and keep cutting on the other side and still maintain your tolerance specifications. But you cannot do that with a fixed caliper. I hope this video has been informative, and I look forward to running lathes and on-car lathes and bench lathes in person in the class. Thank you.